Hello everyone, and welcome to Lecture 6 of QLSC 612. This one's called Introduction to Data Wrangling with Pandas. And even though I tried to lure many of you in with images of cute panda bears, this module is actually not about panda bears. This module is designed to introduce you to the Pandas Python library, which is a really popular Python library for manipulating data that is in tables or in time series. So our aim with this is that the students will build a basic understanding of what is happening underneath the hood of Pandas, and also that you are able to use Pandas practically, that you have the essential practical knowledge to fearlessly tackle the next CSV file or the next type of tabular data that you encounter in the wild. So without further ado, let's get going. So if you open the QLS course materials GitHub and you open the 6th lecture, Data Wrangling with Pandas, you will see there is an intro to data wrangling with Pandas Python notebook here. And you'll probably want to follow along with this as I go through the lecture. We'll also see the exercises and solutions a bit later. If you scroll down, you'll see a picture of a really cute pandas, but that is not what we are speaking about today. So let's go to our Jupyter notebook, and let's start off with a little bit of an introduction. Firstly, what exactly is Pandas? Well, Pandas is a software library for Python, as I mentioned before, and we are not referring to the cute panda bear, the extra cute red panda bear, look at those whiskers, or even the Kung Fu panda bear. Instead, we are speaking about a library that contains data structures and functions to manipulate data that is in tables or in time series. It is built on top of the NumPy library, which I am told you have all seen before. And if you recall, the NumPy library helps users deal with large multi-dimensional arrays and matrices, and has a lot of mathematical functions to operate efficiently on these arrays. In terms of a brief history, development of Pandas started in 2008 by Wes McKinney at a company called AQR Capital, which is a global investment and management firm. So they needed a tool to help them perform quantitative analysis on their tabular financial data. And the name Pandas comes from the term panel data, which is an econometrics term, which is standing for multi-dimensional data involving measurements for a given subject over time. So Pandas actually went open source in 2009, and its official book written by McKinney can be found at this HTML link. This book was published in 2012, and around that point in time, many more developers started joining the project. From 2013 onwards, the project started gathering serious momentum in the Python user base, and it got sponsors, and it grew, and it grew, and etc. And now I'm here in 2023 teaching you about it. So, why does Pandas exist, and when should you be using Pandas? So, why Pandas exists, and why you should care? Well, Python has experienced a huge growth since 2012, and it's been uptaken in a lot of academic settings, such as the one that you're in right now. It's an extremely popular tool, both Python and the Pandas library, and the Pandas library has a very active community of contributors that keep it in good shape. So you can report bugs and they get fixed, and there are new versions of it where they argue amongst themselves and fix things and change their mind and put them back as they were, and it's under constant development, which is a good thing. It's a very well-documented library, so there's this official documentation for it, which is really quite good, and I've stolen a lot of examples from this documentation from this notebook. And there's an official book, as I linked a little bit before, and there's also plenty of Stack Overflow threads and books and online guides and tutorials that are available to help you with your Pandas journey. It features a rich, user-friendly API that, if you are familiar with how Python works, you should find quite intuitive in most cases, and it is a very effective tool to explore your data and to explore and manipulate your tabular data. So computationally speaking, it's definitely faster and less of a headache than your straightforward approaches. For example, using a for loop or a Python list to make your way through a CSV file. And this is due to NumPy arrays being implemented in C, which runs fast. However, it is worth noticing that while it is faster than basic approaches, it is not very fast compared to many database-like tools that are popular in the open source data science world. So if your table gets really, really, really big, we're speaking quite a few gigabytes in size, then you might want to reach for one of those other tools. But if your table fits inside your machine's memory, then you probably want to stick with Pandas. So if you're interested in the other tools, I've linked a few here, and they're benchmarked on a few different sizes of table, and so you can explore them if you're interested or if you might need these someday. It's also worth saying that Pandas is meant for two-dimensional tables, that if you're dealing with labeled multi-dimensional arrays, you might want to check out the X-Array package. So in terms of references and further reading, this module is heavily based on the free Python data science handbook. You can see it here. You can see that the third chapter is all about Pandas. So I've based quite a bit of this notebook on this data science handbook. And if you want a more in-depth coverage of Pandas with more nicks and crannies, then you might want to check that notebook out. It's also good for a few of the other course modules. There's also a very good Neuro Academy lecture on Pandas, which is also based on the same book. So if you don't like how I explain things or my voice or annoys you, then you might want to check out that one too. The first thing I'm going to do here is I'm going to import Pandas and import NumPy. So I'm importing NumPy because I will be explaining some of the underlying structures in Pandas, and these are based on NumPy. So let me just restart this notebook and clear my output. And there we go. We've imported these. The first thing that we're going to speak about technically today are the Pandas objects. These are the objects that Pandas uses to make your life easy when you're dealing with series and tables. So Pandas objects are in essence enhanced versions of NumPy structured arrays. The rows and columns of these objects are identified with labels instead of integer indices. So the first object that I want to speak about, and perhaps the most basic one, is the series object. The series object is essentially a one-dimensional array of index data. So by this point you know what a one-dimensional array is, and we'll speak about the index bit a little bit later. So the series object consists of a sequence of values and a corresponding sequence of indices. The values are a NumPy array, that's simple. And the index is an array-like object of the type pd.index. So we'll discuss that in a bit. And you can access the values and the index of a series object using their attributes. So here I have an example where I'm creating a series from a traditional Python list. So I've got a list here called myList, right? And its values are floating point numbers, 3.0, 5.0, etc. And then what I'm doing is I am using pandas.series, and I'm feeding it as an input this list that I just made. And I'm saving it to the data variable. And that will have created a series. That's simple. You've just made a pandas object, a series. So if I wish to access the values and the index of the series, I will use the values attribute and the index attribute. So you can see that the first thing I did here when I printed data was I printed the series. And you can see that here is my index going 0, 1, 2, 3 on the left. And my values are here on the right, which are the values of the list that we made of my list, 3, 5, 7.2, 9.5. And the series values, which we have printed here and using the .values attribute, are in fact all of those float numbers that were inside our array. And our series index, that index object you can see here, says it has a start of 0 and a stop of 4 and a step of 1. And that corresponds to 0, 1, 2, and 3. And it stops one number before 4. So at this point, you would be completely right to be thinking, so what's the big deal? It just seems like a bit of a glorified NumPy array. And the deal is that NumPy arrays have an implicitly defined integer index. So, however, the series has an explicitly defined index. And this index can actually be of any type you wish, not just integers, as we saw here, 0, 1, 2, 3. It can be other things too. So if you choose not to provide an index when you create a series, like we did here, right? We just fed it our list with no defined index. Then it will default to an integer sequence. That's what we just saw. However, we can also explicitly set the string indices. So I'm going to run this cell right here. And you will see that I'm creating a series, once again called data. This time I feed it the same mylist list with the floating point numbers as above. But this time I've also given it an index input. And this index is an array of the same length. A list of the same length, and you can see that instead of just numbers or being nothing at all, it has a few different gibberish strings that I've just made up here. A, lol, G, B, 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 B. And I'm going to do the same as before. I'm just going to print these series. So you can see that now where the values are in the same, the list values, those floating point numbers. But now the indices, instead of just being 0, 1, 2, 3, now the indices are A, lol, G, B, 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 B. So as you can see, when you explicitly define the indices, they can be pretty much anything you want them to be. And this should remind you of what you saw in the Python lecture yesterday in terms of the key value structure of a dictionary in Python. And in fact, you can also create a series from a Python dictionary. So I'm making pretty much the same dictionary, the same series as above. And this time, instead of supplying a list for the values and a list for the indices, I've just provided one dictionary, right? And it maps A to the values 0.5, lol to the 2.2, G to 3.14, GG to 42.0. Similar concept, slightly different execution. But there you go, right? We have our values, these floating point numbers, and we have our indices, these strings on the left, these explicitly defined index. The next object that we are going to speak about today, and really the steak and potatoes object of this module, is the data frame object, the Pandas data frame. So, if we think back to series, we were thinking of series as a one-dimensional array with generalizable indices. And if we follow this analogy, then a data frame can be thought of as a two-dimensional array, which has generalizable rows, indices, and column names. So, basically what it is a sequence of series. So you stuff a bunch of series together and you make them align such that the series all share the same indices. And this structure is typically used to represent tabular data or just tables. So here you will see that we have a nice big juicy example where we are constructing a data frame from multiple series that have a common index. So the first thing we're going to do is we're going to make 3 different series. So we're going to make these series from dictionaries, as we just saw before. So here we have 3 dictionaries. They have common, well, what will be a common indices when a common index when they are a series for different 3D shapes, right? So we've got cuboids, cylinders, pyramids, cones, spheres, and we have one dictionary with the amount of faces that each of these common 3D shapes has. We have one with the amount of edges and another one with the amount of corners. And the next thing we're doing is we're constructing series out of all of these things, right? So you can see here that we have a faces series, an edges series, and a corner series, where we converted each of these dictionaries into series. And the next thing we are going to do is we are going to make a data frame out of these 3 series. So essentially what we're aiming for is a dictionary where the keys are the column name, yeah? So, and the values are the series. So you can see here that we have our column name faces, and its value is going to be our face series that we made here. Then we have the column name edges, and you can also see that this maps to the edge series from over here. So the key is the column name, and the value is the series that you want to be in that column. And then what we're going to use is the display function to see this data frame that we've just made using the pd.dataframe constructor. So if we run the cell and we go down, we will see that indeed it has made a data frame, a table. And I should note that this display function prints the data frame in a pretty way using HTML code in your browser, but this won't work outside notebooks. It won't work in simple Python scripts. So yeah, that's just good to keep in mind. And these data frames have attributes too. So here you can see that you might want to, for example, get the index labels. So you can print our data frame shapes.index, and then you will see that it gives you all of the different index labels, right? So cuboid, cylinder, pyramid, cone, sphere, etc. You can also then, for example, print your columns to get the column names. And you can see here that we have faces, edges, corners, and that sort of stuff right there. And you can also query for an individual column. So you can use this dictionary style querying to get the faces column, for example. And this column will be returned as a series. And you might want to use this series in the future to shove it into a new data frame or something like that. So you can see that if we do print shapes query faces, then you can see here that it does indeed print out all of the different shapes and how many faces they have. If we're going to continue the dictionary analogy, it's worth mentioning that a dictionary, right, maps a key to a value, as you've seen before. However, a data frame, in a somewhat similar way, maps a column name to a series of column data, which was this creation process that we saw here above, where we're mapping the series to the column name, right? Now, while all of these data frame creation options are similarly instantiated, we're not going to go into all of the different ways you can do this. And if you want to see more ways of creating a data frame, then there are many examples that you can find in the reference and further reading material. So you can construct data frames from a dictionary of series, you can construct them from any list of dictionaries, you can construct them from two-dimensional NumPy arrays and NumPy structured arrays, but I won't go into detail on those right now. The last Pandas object that we will see today is the index object. By this point, we know, and it is clear, that both series and data frame objects contain an explicit index object, and that they use this object to reference and identify their entries. I find it can be useful to think of this index object as an immutable array. That is, an array that cannot be modified after creation. Other than this immutability, you can perform similar referencing and slicing to it as on a regular Python array or list. So if we run this cell here, firstly, we have created an index using the pd.index constructor. We've fed it a list of integers, and we've assigned that index to the variable int. So we can print the index object here. We can also perform referencing, indexing in it, the same way as in regular Python, right? And print out index number 2 and 0, 1, 2. It gives us that 5. Similarly, slicing works like you saw in the Python lecture yesterday. And there are also attributes to it so that you can see its size and dimensionality and the type of objects that are contained in this index. And just to drive the point home that it can't really be modified, if you do try and modify it, for example, assigning the index 2 to the value 2, and you run that, you'll see that it spits a big nasty type error in your face, which you can't do much with. So it's also important to mention, as a bit of an aside, that the index can be thought of as a type of set data structure. We won't go into this in detail as I don't think you've seen sets yet. However, for the more advanced students that know what a set is and how to use it in Python, this is good to be aware of. And you can use the Python set methods on these index objects quite a bit. That brings section 2 to a close. So that was the more theoretical part of this lecture. Hopefully at this point you know what an index is and what a series is and what a data frame is and how they are constructed and how they build up a data frame. And now we're going to go into slightly more practical things, and I've called this section the Pandas Wrangler Essentials. And you won't be wrangling panda bears, but you might be wrangling some rather unruly CSV files. So the first thing that we're going to see here is data I/O, so data in, out. Basically how to read and how to write files using Pandas. One of the most common scenarios you will encounter is reading in a CSV file, right? There's a CSV file with a table in your dataset with a bunch of phenotypic data or something like that, and you need to read it in, do some queries of it, etc., etc. So if you specify a web address or a local path, Pandas can read in this CSV file. And there are also methods to read in other file formats of tabular data. I focus on CSV because, in my experience, it is the most common one by far in the duration of my PhD, but check out the documentation if you have some other weird format of table that you might want to open with Pandas. So, using the Pandas read CSV function, you can read in a CSV file. And in this case, I've just found a CSV file that looked interesting on GitHub. And I have provided the link to it here, right? This .csv addresses.csv file. It's just a thing on the internet. If I grab this link and I copy it and I paste it, you will see that it is a CSV file. And then what I'm doing, so we're going to run this cell, is I'm using the display function to show the head function of Pandas. And what the head function does is that it returns the first few rows of the data frame. By default, this is 5 rows, but if you change what is inside of the argument, then you can see that you can get, say, 10 rows or more rows or less rows. But yeah, you can see that we have successfully read in this CSV file as a Pandas data frame, which is good. And at this point, you might be wondering, okay, that thing is indeed a table, but it's rather large, and I just need a couple of the columns of it. So what can I do? Well, you can add an argument, the useCalls argument to it, to specify the columns you want to read in. So say I'm only interested in the ID column, right? This one here on the left, and the postal code column here. And then we're going to go ahead and display the head. And you will see that the table it has imported only contains the ID and postal code columns. If you want to export your data frame to a CSV file, then you can use the toCSV method. Likewise, you can export to other formats too. You should check the documentation on how to do that if you want to do it. But you basically just need to have your CSV data frame, right? So you're going to have your data frame. In this case, we have it in the CSV data mini variable. And then what we're going to want to do is we're going to want to use the toCSV method. And then in the first argument, you're going to name your file, and then you are going to set the index to false. That is, unless you want the index to be inside your CSV file, in which case change it to true. But in this case, I'm going to say we don't. Then I'm going to run it, and let's check out the output. So I've got this in LibreOffice here, but you can see that our CSV file does indeed have just an ID and a postal code. Yeah, this is a LibreOffice calc, which is basically a free version of Excel. And yeah, you can see that our CSV file is exported successfully. This next section is called Selection and Indexers, and some other nuts and bolts. It's one of the more dense sections of this notebook, but also a really useful one, so you'll want to pay some close attention. So at this point, you've probably either read in a CSV file and you've got some tabular data loaded up in a Pandas data frame, or you've constructed a data frame. Fantastic. Now this next step is that we will probably want to select data within these data frames that we want to access and process or do stuff with. In Pandas, selection of data is done with indexer attributes, so with indexers. So well, if you play enough time with Pandas, you'll notice that it is possible to select entries in series and data frames using list-style indexing and slicing. This is bad practice, and you should avoid it at all costs. By list-style indexing and slicing, I mean this: when you use the square brackets to directly access elements of your series or data frame. And the reason that you want to avoid this is that it is often a source of great confusion, wailing, and gnashing of teeth. And this is because in a series with an existing explicit integer index, then referencing, for example, data 1, will use the explicit index that the user has given. However, printing data 1 to 3 or accessing the slice of data between 1 and 3, elements 1 and 3, will by default use the implicit index, the integer index of this Pandas object. And the way that Pandas deals with this confusion, and to make it slightly clearer for people, is providing indexer attributes. So there are two main indexer attributes. There's some other ones that if you want to read about, you can see the documentation. But for the main practical purposes of this course, there are two that you will use a lot. There is the loc, standing for location, that always references an explicit index. And then there is the iloc, or integer location, which always references the implicit index, so that integer series that goes with your values. Here we have a table, and you can here we have a cell, and you can see that we've constructed a series in it, right? So we have some values here, which are just strings, and then an index of integers that we have explicitly defined as being 1, 3, and 5. And we're going to run this cell. So we print out just our series object. You can see that here it is, indices 1, 3, and 5, and values hi, hello, hey. Then if we reference the first element, so data square brackets 1, you will notice that it does so using explicit index. So here we have explicitly defined an index with a list, and it goes and it finds that this 1 that we have explicitly mentioned that we want, and it says, okay, that's the first element of this index. So it goes to the first element of value, and then it says the first element of the values is hi, and it prints out hi, which is very kind of it to say hello to us. However, as you will see, this gets quite confusing, because then we might want to do the exact same thing, but we just want to do slice instead of referencing a single element. So say we want to slice from positions 1 to 3. If we are using the explicit index, it would just print hi and hello, right? Because 1 and 3 in the index corresponds to the first two elements, hi and hello. However, it is using implicit index when slicing. So it will use regular list style slicing, corresponding to that implicit integer array. So elements 1 to 3 it starts at 0, and then 1 to 3 would correspond to this 3 and 5 elements, right? These here. And we can see that it prints them here. So 3 and 5, hello, hey. And as you can see, that it would make it very easy to get mixed up if you're dealing with explicit or implicit indices, and therefore we just suggest to avoid this altogether. And instead, you'll want to use the much more consistent loc and iloc attributes. So we have our same data series here, and you'll see that if we print out loc1, then we're going to have the explicit index 1, so hi. And if we use iloc instead, then it's going to use the implicit index, or the second element, which as you can see is hello, and indeed it goes for hello. And if we want to do slicing, similar. If we want the explicitly defined index, and we want to slice between literally elements 1 and 3 in our defined index here, so 1 and 3, hi, hello, then you can see that it's going to give that. And if you want to use iloc, or your integer location, for implicit referencing, then you will see that it will do that, and it will give us that 3, 5 that we were confused about last time here, this 3, 5, hello, hey. So that is very important to take into account. We can also, in a similar way, set values inside of a data frame or a series using loc and iloc. So if we have data.loc and then we index 1, we can set the explicit index of 1 to sup. So we run this cell and you can see that what we have defined for our explicit index of 1 that used to be high has now been updated to sup. And I think it would be very useful to show how these index attributes work not just with a one-dimensional series, but with two-dimensional data frames. So remember our shapes data frame? Yeah, remember that's what it looks like. Well, we might want to refer, perhaps do some slicing on it using our iloc or the integer, the implicit indexing. And you have to remember that this is usually given with rows and then comma and then columns. So if we run this cell, you will see that we want all the rows until the third one and all the columns until the second one. And it has indeed given us the first 3 rows of cuboid, cylinder, pyramid, and the first 2 columns of faces and edges. And then the equivalent way of doing this using the explicit labels or loc would be to say I want all the rows until pyramid, right? Because 1, 2, 3, well, that's the third one. And then all the edges, all of the columns until edges. So 1, 2, and you'll see that these are equivalent data frames. So it's just showing 2 different ways that you can produce a subset of this data frame using iloc or loc, depending on whether you find it easier to just access things using the integer index or the explicit index that we have defined. So it's a good example to study a bit and keep in mind, and you'll probably find it quite useful. While we are on the topic of selecting and modifying information in data frames and series, it's crucial to bring up the concept of deep and shallow copies, because this can cause a lot of pain and gnashing of teeth and wailing and tears if you are not careful and aware about it. And to explore this example, we're going to go a bit back to that addresses CSV that you read in the Pandas. And if you remember, we read a couple of columns, the ID and the postal code from that CSV file, into this CSV data mini variable. Let me just display it here for the sake of clarity. Yeah, so you remember it there. When we are retrieving a series from a data frame, you will see that you can do it using the loc function as such, right? So for our row, we're saying grab all the rows, and for our column, we're saying grab the postal code column. And then if we print, for example, this series that we have read in, just this one postal code column as a series, then you can see it prints here some indices and the values of this series. If we want to print out its keys, then we can see its keys and its indices as such. And if you want to see the index and the postal code packed into a tuple, then you can print out the items, which can be useful to iterate over and unpack things manually if you wish to do so. However, this gets interesting because say now we wish to modify the first value in this series, right? So we have this first value here with the index 0 and the value is 94,063, and we want to change it to 666 because Iron Maiden. So then we go and we print it and we change it, right? And we've printed our series again after having changed this, and we can see that we did successfully change index 0 to 666 using the loc indexer. And this is great, right? We've done the change we want to, but not so fast. Modifying the entry has given us a weird warning here. A value is trying to be set on a copy of a slice from a data frame. What does this mean? Why is it red and angry? Why should I care? Well, this brings us to the concept of returning a view or a shallow copy versus a copy or a deep copy. So a view, otherwise known as a shallow copy, does not have its own data. So it views the data that is contained in the original array. It is just seeing and sharing this data with the original array it was obtained from. And therefore modifying the view modifies the data in memory of this original array. And you end up modifying the original array even if you did not want to. Meanwhile, a copy, or a deep copy as it's known, create a separate instance for the copy you have just made. So the original array you've accessed this information from and the copy are two completely separate instances in memory, and you don't have to worry about modifying the original by modifying your copy. So in Pandas, and more generally in any Python functions you use, make sure to check if the method that you're using returns a deep or a shallow copy of an object. Or you might end up modifying things you didn't intend to. So for example, we got that series value, right? We got this code series. We got it from our variable data frame, CSV data mini. And you will see that if we now print it, well, indeed, this first element has changed to 666. And perhaps we didn't want that. We just wanted to modify it in this series that we nabbed from the data frame. We didn't want our original data frame to change. That's quite chaotic, especially if you're not aware it's going to happen. So if you wanted to leave the original data frame intact while modifying the series that you just extracted, what you need to do is make a copy of the series. So just for the sake of clarity, we're reading in the CSV again. We're creating the CSV data mini variable with the data frame afresh because we messed with it here, as you can see, and unintentionally modified it. So now we're just reading it again from the source on the internet. And now we are making pretty much the same thing. We're saying use a loc to grab all the rows and the postal code column. But what we're doing differently than before is we're adding this copy functionality to the end of it. And by doing this, we are making a deep copy of the series from our data frame, and not just a shallow copy which shares the data with CSV data mini. Instead, we will have our own entirely different series in memory to represent this data. And now, when we change the first element, the loc 0, to be 666, we will see that if we access the CSV data mini variable and we see the data frame, well, it is still intact. Our first element is still what we wanted it to be. So that's very useful to keep in mind. And to end off this section, I'll just show you a couple of other additional useful little tricks that you'll probably need sooner rather than later. So if you have a functional data frame and you wish to add a column to it, you can simply assign things to the inexistent column. So if you'll recall our shapes data frame, there was absolutely no such thing as a ratio column, just faces, edges, and corners. However, if we access and we query for that ratio column, and then we define it here as whatever we want, but in this case, I'll also show you some vectorized operations where we are dividing the faces value by the edges value, then you will see that we will indeed add a column with this ratio to our shapes. And there it is, right? We've now added a ratio column. This was just done by using our square brackets to access the ratio column and create it in the process of doing so. And then we say, well, this ratio column is a little rubbishy. Actually, I want to delete it. It's very common to want to delete a comment. So what you need to do is use the drop functionality here. And then we are saying drop, and you can provide a list of columns to drop. In this case, it's just the ratio because we don't like it very much for whatever reason. And then you need to specify the axis that you are dropping things along. So if you drop things from axis 0, you're dropping it basically from your index, from your row. And if you drop from axis 1, then you're basically dropping from your column labels. And you can see that after we have dropped ratio on axis 1 or on the column axis, we are back to our original frame shapes data frame, which is good. So the next thing I want to show you is iterating through the rows of a data frame with a loop. And this is usually not recommended. It's not a very efficient way to go about things. It's better to use a vectorization from NumPy to do this sort of thing. But sometimes if you have just an extra entangled and complex data processing procedure, you might need to do this. And it is quite simple to do. You simply you loop over iterRows. So use the iterRows attribute, and then you can access the index and the rows as such. So you can see here that it prints out basically for a cuboid the faces, the edges, and the corners, right? And it simply goes through all the different rows: cuboid, cylinder, pyramid, cone, etc. The next thing we're going to speak about is filtering in Pandas. And by filtering, I mean finding the rows in a dataset that satisfy a specific condition. Perhaps the data frame that you are working with has the ages of different subjects and the different conditions they have. And for example, you want to find all of the subjects above age 50 or, something like that. So if you will, recall our shapes data frame. It's really tough to type and to speak into this microphone at the same time. So that's why I sort of go slow whenever I'm typing. But if you'll recall, here is our shapes data frame. And say, for example, you wanted to find all of the shapes that had more than 3 faces, right? So this is a small table, so it's easily you can inspect and just see, the first 3 have more than 3 faces, right? The cone and the sphere don't, but cuboid, cylinder, pyramid do. So if you had a really big table, you wouldn't just be able to do that by hand. So you could use some filtering, such as the one done here, to find that cuboid, cylinder, and pyramid that have 6, 4, 5, more than 3 faces, right? And the right way to do that is you use loc once again on your shapes data frame. Then inside the loc query, you specify that you want the attribute faces and you want more than 3 of them. I think it's not clear here, and it is also important to mention that you don't necessarily have to use the attribute. You can also do a dictionary style reference here. So if you do that, you will see that it gives us pretty much the exact same table. So these are 2 ways that you can do the same thing, 2 alternate ways. You can either use the attribute or a dictionary style access here, and both will work just fine. And they will give you the shapes that have more than 3 faces. And oftentimes what you want to do is you want to have a composite query, a more complex thing that satisfies multiple conditions. So you can chain them, and you can chain them using either your dictionary style accessing like here, or your attributes. It doesn't really matter, but what does matter is that when you're chaining them, these different conditions to each other, you'll want to use bitwise AND or a bitwise OR, as opposed to the logical AND and logical OR that you have been introduced to so far. So that's the logical AND and that's the logical OR, literally spelling out the words. That won't work. And if you try and do that, then it will try and convert your series to booleans and raise an error. Try it if you don't believe me, just change that to an AND. So yeah, use this bitwise AND, the ampersand, or this vertical bar, which is the bitwise OR, right? So here we have a query. So we've saved our query to this query variable, so it doesn't just disappear into the nether after we're done displaying it, like we did previously. And then we can display this more complex query where we've used the loc indexer to find shapes that have more than 3 faces and that do not have 12 edges. And you will see that the only such satisfying shapes are the cylinder and the pyramid. And you can chain many, many more conditions. So this is useful to identify rows that you can use and that you want to use. The next thing we're going to speak about today is combining data frames. And this is a very important topic because, for example, what would you do if you wanted to filter across 2 data frames? Say there were 2 separate CSV files in your study. One of them had the age of the subjects, the other one had some other condition you wanted to filter for, but they're in separate data frames and it's hard to deal with that. So you just want to join things into one data frame. And there are a couple of different types of combinations. There's more than a couple, actually. It's quite a few. But we're going to focus on a couple that are the main building blocks for these different types of combinations. The most important ones for you to understand. The first one is the concatenation, or the concat function. And you literally just stick together, you splice together 2 data frames along a chosen axis. And then the second type is the merge, which is more powerful, and it allows you to combine data frames by aligning the rows from each of the 2 data frames based on common attributes or column values that they share. There are more types of ways to combine data frames in Pandas, like append and join, but these just tend to be shorthands for certain parameterizations of concat and merge. Merge in particular, we're just scratching the surface of the tip of the tiny microscopic jagged edge of the iceberg. It's really powerful. It implements a subset of relational algebra, a procedural query language that I can't claim to be an expert in, but basically provides the formal rules for manipulating relational data, which is a foundational building block of many database softwares beyond Pandas. The examples in this section I've straight up stolen from the Pandas documentation. I highly recommend you read over it because we are not going into much depth here and this is very useful stuff. But yeah, we'll see a couple of basic examples to show you how this works. So in this first example that I'm running here, we have one data frame that we've called data frame 1, df1, right? You can see here that we've defined it as a dictionary and we have letters as keys and then a list with the numbered versions of these letters as values. And we have indices 0 to 3 here as a contiguous integer list. And then we have a second data frame, df2, where we're doing similarly, but now the numbers for each of these key values goes from 4 to 7 instead of 0 to 3 as in the data frame 1, and our indices also go from 4 to 7 just for the sake of illustration. And then say we wanted to concatenate these, right? So one on top of the other one in this case. You can also do it side by side, but for this example let's do one on top of the other one. Then what you would do is you would place both of these data frames inside the list as done here. And then you would pass that list to the concat function. And along with that, you also have to provide an axis. So if you want to do the concatenation along the rows, so meaning vertically stacking these 2 data frames on top of each other, you provide axis 0. If you want to do it along the columns, so horizontally stacking the 2 data frames one after the other, then you'd put axis 1. But here we can see our first data frame, right? Just as we defined it. It has our columns, which are A, B, C, D. Our entries are numbered according to the row values here. And we similarly have the same for our second data frame, A, B, C, D, and 4 to 7. And what we just asked this to do with the concat function is stack them into one single data frame vertically. And as you can see, by doing this through axis 0, it was achieved. And now our data frame, our result data frame, goes from 0 to 7 in these row values and A, B, C, D in these column values. And that is a good way to join these two. For example, if half the subjects were in dataset 1 and another half of them were in dataset 2, that would be a good way to join them into one dataset. So the next way to combine data frames that we're going to see is the merge function. And we're going to start out by explaining this with a simple example. We once again build two data frames, in this case left and right from dictionaries. And you'll notice that our left data frame has keys or column values of key 1, key 2, A, B. And our right data frame has the same key 1, key 2, but a different C and D column. And here you will see that we have our merge function, right? And our merge function, we're merging the left and the right data frames, and we're merging them on key 1 and key 2, so these keys that they have in common. And we are using the default inner method, but there are quite a few different ways of doing this. Left, right, outer, inner, cross example. This particular inner method uses the intersection of the keys in both of the data frames to produce the result. So if we run it, we'll see what this looks like in more detail. Using the pretty printing display, we can see that for our row 0, row 1 and row 2, we have keys in common, right, between the two data frames. So left has K0 and K0 for key 1 and key 2. Right has the same. Left has K0 and K1 for key 1 and key 2. And left has K1 and K0. The order is different, but for this particular type of merge, that's not an issue. And likewise, for the third row here, it has K1 and K0 for key 1 and key 2, and K1 and K0 for key 1 and key 2 in both data frames. And then if we display the result, the merge, you'll see that the intersection of these two on key 1 and key 2, so the things that are in common in key 1 and key 2 are kept and are merged based on that, and the rest are discarded. And this is what the result looks like. So key 1 and key 2 that we established, these three rows have elements in common, are there. And then A, B, and C, D are now in the same data frame, whereby they used to be in different data frames. And they were merged based on the values that they had in common for these key 1 and key 2 that we specified we were merging on. I find this is quite a tricky method to just explain in words, and I think that the best possible way you could go about truly understanding merge, because it is really powerful and convenient, is first to read the documentation in good detail. They have quite a few examples here, some complex, some simple, but there are really lots and lots of examples for you to see and how the different methods work. And definitely feel free to play around with how they work, because it's a little more abstract, I guess, than just concatenation, where you splice two arrays together and you're finished. But I hope it's clear what's going on and how the data frames are being combined based on column values that they have in common. The last thing we're going to see today is a bit simpler, and it is simply the inbuilt aggregations that Pandas features for series and data frames. So efficient summarization of your data is important for your analysis. And in terms of inbuilt aggregations that Pandas offers, when you're not just constructing your own ones, which gets a bit more complex, this can mean things like the mean, the sum, the median, the standard deviation, etc., of your different series and data frames. So we're just going to cover some very basic inbuilt ones today, but we won't have time to cover how to make your own. For that, I suggest you read about the concept of a group by and a split apply combine in Pandas. One word of caution I would like to say, if you do proceed to read up on this, is don't worry too much about the formalities of this. Split, apply, and combine are just things that make the life of a developer easier and more efficient. But by just using your own intuition, you will find that this split, apply, combine strategy works pretty easily and flows naturally. For example, you already know how to copy a series from a data frame, filter it to find the parts you're interested in, and compute something on them. And then perhaps how to add that column to a data frame with your computation results. And this is, in crude steps, exactly what the split, apply, and combine is. So you can do this with your own intuition too. But in terms of built-in aggregations, well, here we have, we're creating a series creatively called a series. And we've just put 1, 2, 3, 3 into a list and made a series out of them. The describe method is very useful because it just shows you many common aggregations all in one. So you can see the count here, the mean of this series, you can see the standard deviation, minimum, different quartiles, the maximum, etc., etc. Value counts is also a method that is very popular. And with value counts, you can count the unique values inside your series. So it tells us that the value 3 occurs twice, right? And that 1 and 2 only occur once. And similarly, you can also just call the describe on a data frame. So you will recall this shapes data frame that I've based a lot of my examples on. And you will see that if I call the describe on it, then it gives us, for each of the columns, faces, edges, and corners, the mean and the standard deviation and all of those same common values. And you might just want to have one individual value of these. Say you might just want the median, right? Or you might just want the mean or something like that. So typically you can just use these functions as such, call for the count, call for the median, and you will be able to see these aggregations for your data frame or for your series. And then the only thing left to cover is, for example, what if you want to aggregate across a row in a data frame? And then in that case, you can simply compute the aggregation you want, say the mean, across a different axis. So you can specify 1 as 0 or columns or rows. And that is that. So I hope this lecture was easy to follow along and that it was somewhat entertaining and you learned something from it, and that the next time you have to use a CSV in Python and process it and do things with it, you won't be too scared and you'll be able to do stuff with it. And as a bonus, here are some Pandas pictures. Here's a glorious Star Wars one, and here's probably what you guys will look like after QLS 612 is finished and you've had all that information crammed into you in a week. And here's the red pandas once again. Look at its whiskers.